Hello, and welcome to this video on the topic of transformers. Previously, we saw how transformers allow for the efficient transmission of electricity across distribution networks such as the national grid. Here, we're going to find out how they work. Have a look at this setup. A coil, a cell which supplies DC, and a switch are attached to coil 1, and a sensitive center zero ammeter is attached to coil 2. When the switch is closed, the ammeter needle flicks to one side before returning quickly to zero. When the switch is opened again, the ammeter needle flicks the other way before going back to zero. What's going on here? Let's try that again, but a bit more slowly this time. When the switch is closed, current flows through coil 1, which means that a magnetic field is created around it. The flux lines of this magnetic field cut through coil 2. Because the magnetic flux through this coil is changing, a current is induced in it. When the current in coil 1 stabilizes, the magnetic flux through coil 2 is no longer changing, and so a current is no longer induced in it. When the switch is opened again, current no longer flows through coil 1. This causes the magnetic flux through coil 2 to change again, decreasing to zero. While this magnetic flux is changing, current is again induced in coil 2, but in the opposite direction this time. When the magnetic field through the coil falls to zero and stops changing, the induced current stops flowing and the ammeter reading returns to zero. In the previous video, we saw that moving a magnet towards a coil of wire led to the generation of an induced PD across the coil, as the magnetic flux through the coil was changing, or the field lines were cutting through the coil. When the magnet was held still, the magnetic flux through the coil stopped changing, and the induced PD fell to zero, and when the magnet was pulled back out of the coil, a PD was again induced across it, but in the opposite direction. What we've seen happening here in the second coil is pretty much the same process, except that here, the magnetic flux through the coil was being changed by changing the current in a nearby coil, which in turn changed the magnetic field around it. This is the process which allows a transformer to work. A little more detail now on how a transformer is constructed. A transformer consists of a primary coil, a secondary coil, and a soft iron core which is easily magnetized and demagnetized. When alternating current is supplied to the primary coil, an alternating magnetic field is produced around it and within the iron core. This changing magnetic field causes an alternating PD to be induced in the secondary coil. A current will not be induced in the secondary coil when a direct current is supplied to the primary coil. In other words, transformers need AC to work. If the current in the primary coil doesn't change with time, then the magnetic field around it won't change either, which means that its lines of magnetic flux won't cut through the secondary coil. This transformer is being supplied with AC. It might work, and it might look nice, but it isn't actually doing anything that useful right now. Okay, so the flow of an AC in its primary coil allows for the induction of an AC in its secondary coil. Cool magic trick, but what's the point? The point is that by playing around with the number of turns on the primary and secondary coils, we can start to do some pretty useful things with our transformer. By doing so, we can produce one of two different types of transformers. Step-up transformers have more turns on the secondary coil than on the primary coil, and so they increase the PD of an AC supply. The other type of transformer is the step-down transformer. Step-down transformers have fewer turns in the secondary coil than on the primary coil, and because of this they decrease the PD of an AC supply. The equation which allows us to work out the effect of having more or fewer turns on the secondary coil of a transformer than on its primary coil looks like this. Vp over Vs equals Np over Ns, where Vp and Vs are the potential differences across the primary and secondary coils, and Np and Ns are the numbers of turns in the primary and secondary coils. If we rearrange this equation to make Vs the subject, we can see mathematically how step-up and step-down transformers work. In a step-up transformer, Ns is greater than Np, so this term will be greater than 1, which means that Vs is greater than Vp. In a step-down transformer, Ns is less than Np, which means that Ns over Np is less than 1, and so Vs will be less than Vp. If that all sounds a bit mathsy, don't worry, because these examples will show you just how easy and enjoyable this equation is to use. Example 1. As you can see, Joanna is trying to power a 12-volt bulb. There are 4 turns on the primary coil and 12 turns on the secondary coil of the transformer. In part A, we're looking for the primary PD, which will give a secondary PD of 12 volts, so let's give it a go. Our equation again is Vp over Vs equals Np over Ns. Then subbing in, we have Vp over 12 equals 4 over 12. From here, you can work out Vp whichever way you like. What I'm going to do here is to multiply both sides by 12, or to bring this 12 across to multiply, so that gives us Vp equals 4 times 12 over 12, which gives a final answer of 4 volts. For part B, this will reduce the brightness of the bulb because it'll cause the primary PD to be stepped up by a smaller amount. Can you prove to yourself that when there are 8 turns on the primary coil, the PD across the bulb will only be 6 volts? Have a look through example 2 now. Our equation again is Vp over Vs equals Np over Ns. Here we're looking for Ns, so let's make it the subject of the equation. That gives us Ns equals Np times Vs divided by Vp. Then subbing in, we have 22,000 times 230 divided by 253,000, not forgetting there to convert from kilovolts to volts for the equation, and that gives a final answer of 20 turns on the secondary coil. In a transformer, electrical power is transferred from the primary coil to the secondary coil. If the transformer is 100% efficient, all of the power which is supplied to the primary coil is transferred to the secondary coil, and we can write down a power transfer equation which looks like this. VPIP equals VSIS, where Vp and Ip are the PD across and current in the primary coil, and Vs and Is are the PD across and current in the secondary coil. The left-hand side of this equation represents the power supplied to the primary coil, and the right-hand side, the power transferred to the secondary coil. Real transformers aren't actually perfectly efficient, but with careful design, they can come pretty close. In this example, as you can see, a phone charger is being used to deliver 5 watts of electrical power at a current of 1 amp, and in part A, we need to work out the PD across the output terminals of the charger. The electricity equation to use is of course P equals VI, then subbing in we have 5 equals V times 1, so V must be equal to 5 volts. In part B, as you can see, the charger is being powered by a 230 volt AC supply. Hopefully you'll see that this is Vp here. We've just worked out Vs. We've been given Is in the question, and we're looking for Ip, so let's give it a go. Writing down our equation, we have VPIP equals VSIS, then subbing in, that becomes 230 times Ip equals 5 times 1, and so Ip, the current in the primary coil, equals 5 over 230, which gives an answer of 0.022 amps. To 2 significant figures. You might have spotted here that the right-hand side of this equation gives us the power in the secondary coil, so we could have subbed 5 watts in here and got the same answer. One last example now for this video. As you can see, the generator is supplying 50 megawatts of power at a PD of 25 kilovolts, and in part A, we're looking for the current which it supplies. Using P equals VI and rearranging, we end up with I equals P over V, and subbing in, the power is 50 megawatts, which is equal to 50 times 10 to the power of 6, or 50 million watts, divided by a PD of 25 kilovolts, 25,000, or 25 times 10 to the power of 3, so that gives a current of 2000 amps. For part B, our equation is Vp over Vs equals Np over Ns. You can do this one whichever way you're happy with. What I'm going to do here is to make Vs the subject of the equation, which looks like this. Vs equals Vp times Ns over Np, and then sub in my numbers. 25,000 times 100,000 divided by 10,000, And that gives an answer for Vs of 250,000 volts, or 250 kilovolts. Have a look through parts C, D and E now. In part C, our equation is VPIP equals VSIS, then subbing in that becomes 25,000 times 2,000, which was from the previous screen, equals 250,000 times IS, which is what we're trying to work out. Doing the maths then, we see that IS must be equal to 200 amps. So by stepping the voltage up by a factor of 10, we step the current down by a factor of 10. For part D, we need to use the equation for the power dissipated in a resistor, P equals I squared R. Here, the resistor is the cable itself. Subbing in our numbers then, that becomes 200 squared times 20, which gives an answer of 800,000 watts, or 800 kilowatts. In part E, finally, if a step-up transformer hadn't been used here, then electrical power would have been transmitted down the cable at a current of 2000 amps instead of 200 amps, which would have increased the power dissipated in the cable to a staggering 80 million watts. Because P is proportional to I squared in this equation, increasing I by a factor of 10 causes P to increase by a factor of 100. It's for this reason that transformers are such a vital part of the national grid. Without them, far more electrical energy would be dissipated as heat in power cables, which would make the whole system much less efficient, but more polluting and more expensive for the consumer. That brings us to the end of this video and this topic. If your appreciation of physics hasn't been transformed by now, I'm not sure what else I can do here. Just kidding, I know you loved it all along anyway. Thanks for watching and good luck.